Well, let's finish this calculus chapter. So lesson 12.6, the fundamental theorem of calculus. And where we're going to pick up is this Bellringer. Last class we learned how we could approximate the area of a graph of a function between the function itself, or the curve, and the x-axis on any interval. And so I kind of built a calculator for us last class, and you can find this if you just go to your calculator list at the very bottom. You'll see that link. And to show you how it works, what we're going to do is type this equation in as f of x. So I'm going to have negative 1/3 x squared plus 2x plus 1. And we want to estimate the curve, or the area between 0 and 5. So right here on the A and the B, I want to put that to 0 to 5. And so last class, what we talked about is there different methods of going about this. We could do what's called the Right Riemann Sum, which is basically you're adding up these little rectangles, and you take the right endpoint all the way through, and I need to add the 0.5 on here. So from 0, or we actually would start with the rectangle that completes at the x value of 1, and then 2. And this is if you had a width of 1, and you would find the area of each rectangle, multiply them out, and you would come up with your area. So in this particular case, we would be adding the areas of 1 times each of these amounts here listed. So it's like 2 2/3, 3 3/3, 3 2/3, 4, 3 2/3, 2 2/3. You would add those up for your total area. And as the lesson went on, we learned that you could do that's a right Riemann sum, is what that is. And we could look at it as a left Riemann sum, where you're taking the points on the left side, and you would add up these rectangles. And then finally, when we got clear to the end, we got the formula for how to get a better understanding of the area by shrinking the width of each one of these Riemann sum rectangles. And so if I go to right Riemann sum first, when I click this, you will see that the area as shown here, if I added up those 2/3 I was talking about, is represented at this value. It'd be 16 2/3 if you added up these values from 0 and where'd my 5 go? There it is. If you added up 2 2/3 plus 3 2/3 plus 4 plus 3 2/3 2 2/3, you should get 16 2/3. That would be the value there. But you can see that this area will not be accurate because we're missing some space over here. And on these 3 blocks, we have extra area added in. And so the exact answer we learned is by using this integral. But what I want to show you what it does is basically the theorem that we learned about last class is it starts shrinking these rectangles to make their width smaller and smaller and smaller. You might have saw I just changed that letter to a W for width. And what happens is the smaller that the width of each of those rectangles gets, the closer the area to being exact, the area under the curve. As you can see, as I make this smaller and smaller, it becomes more and more accurate. Now we're getting really, really close. And I'll go as small as it can. And you can see this looks pretty well like the actual area. And that's basically, in essence, what happens when you take an integral. It just shrinks these rectangles from being 1 unit long, or however long you start, to as small as possible, infinitely small rectangles, if you will. And that's how it calculates the area. So in this particular problem, we should get the answer of 145/9, which if I turn off the fraction is 16.1 repeating. So the answer would be C here. And as a reminder, if we took the right Riemann sum with blocks length of 1, that's what that 16 2/3 would have got us, which would have been an overestimate. And so now we'll try number 2 here. It says the garden in the shape of regions shown below. If each unit in the coordinate system represents 1 foot, approximately how much area does the garden contain? It'll be square feet because it's feet times feet, which is feet squared. So here's my curve. I'm looking for the area under that curve. So I'll come to my equation up here. It's 1/2 x plus 4. And it looks like we're looking on the interval from the x value of 1, 2, 3, 4 to 5. 1 to 5. So I'm going to change my A here to a 1. Okay. And so there's my right Riemann sum. Whoa. There would be the right Riemann sum estimate. And this would be adding up the areas starting from the second from the x value that ends in a 2, 3, 4, 5. And so you would be looking at starting the 2, 3, 4, and 5. You'd be adding these together. That's 21, 33, 46, I believe. Let's check that. Well, why is it saying this? I'll have to check through to make sure. From 2 to 5. So this would be 1 times, it has a height of 5 here. So 1 times 5, that would be 5. So I'm not sure exactly. Oh, I see what I did. I did need to correct this math. This should be W minus A1. That'll correct the math. There we go. And so now you can see the correct values that you'd be adding together. You'd be adding 5 plus 5.5. That's 10.5, 16.5, 23 even. And that's where it gets that value. Okay. And that would be the width at 1. Now, if you wanted to approximate what's the area, if these blocks got infinitely small, what would happen is you'd have this, and you'd have to, if you're going to use the table, add in all the values in between, which we're not going to do. What I'll just show you is the actual value would be 22, not 23, but 22 feet squared. And that would be our answer.